In this section, let's take a look at how we solve exact equations. Before we can get started with solving exact equations, we have to consider some preliminary information. This preliminary information, if you have already taken a Calculus 3 course, multivariable calculus, is largely a review. If you have not yet taken it, don't worry, we're going to cover all of the basics that are necessary. It won't be as deep as you would do in a Cal 3 class, but it will be sufficient to understand this topic. Okay? So here I'm going to say review. And here this is assuming you've already taken Cal 3. If you have not taken Cal 3, well then clearly it's not a review. And you will see it again if and when you take that course. So definition. Let's say you have a function, as is customary, we'll call it f. And let's have that be a function defined on an open region of the xy plane. So it's a function of two variables. Okay. For that multivariable function, we can take a derivative of that function with respect to the variable x. There are two variables, but for this computation, we consider only the first variable, x. And the definition of that is, well, it's pretty much the definition that we always have for a derivative. It's a limit. It's the limit as h approaches 0 of f of x plus h, comma y, because after all, you do have two variables. You're only considering what happens as you change x, but y is still there, even if it's not changing. So it's the limit as h approaches 0 of f of x plus h, comma y, minus f of x, comma y. Again, notice y never changed, only x does, over h. This is called the partial derivative of f. With respect to the variable x. On the other hand, if you take this notation here, this is with respect to y, this is the limit as h approaches 0 of, and now y is what's going to be considered, so x will just stay constant. It'll stay, it's still a variable of the function, we just don't consider it changing. So x is going to stay x for both of these, but this one will be y plus h, and this one will just be y over h. And this is the partial derivative of f with respect to y. The phrase with respect to, if you're not familiar with the abbreviation, is often abbreviated as WRT, because frankly, that's not something we want to write out every single time. With respect to y. This, of course, is provided that the limit exists, because just like you see in a Cal 1 and a Cal 2 course, sometimes limits just don't exist for a particular setup. So here, provided the limit exists. Now, as far as computing a partial derivative, of course, one thing you can do is go by the limit definition, but that's not the way most people do it. In fact, the way most people do it, there's kind of a short heuristic, a shortcut, that you consider what this definition is saying, and you take it really pretty literally. So let's say I have the function of two variables, I'll say x, example, I'll say x squared y to the third plus the sine of xy, like that. Now let's say I want to take the partial derivative of this with respect to x. Note that we don't have prime notation here. We don't say, this prime, because that wouldn't make any sense. If you just said, I want to take the derivative and then I write prime, I don't know which derivative I want. So here we use this notation to clearly highlight which variable is being considered. Okay, so don't use prime for this. So here we take the partial with respect to x. Now, of course, we could go through this process, but instead what we're going to do is we're going to consider this taking this a little bit more literally than you might expect. Here, your function is changing its value on x. The value of y isn't changing from this part to this part. Well, what do you call something that doesn't change? Oh, well, that's called a constant. Okay, so for the sake of taking this limit, y is a constant. It never changes. H changes, and x changes because you've done something to it, but y never changes in any way. So the short way of taking a derivative with respect to x is to consider y as a constant. And I mean that literally. Here, y to the third, just think of it as like the number 5, or the number 12, whatever number you like. Here, whenever you have a constant, and in fact, let's do this to the side. If you were in a Cal 1 class and I told you I have 5 times x squared, and I asked you to take the derivative with respect to x, well, you wouldn't even touch the 5. You would just take the derivative of the x squared, giving you a 2x, and then you'd multiply those, giving you 10x. Same thing here. This is a constant, just like the number 5 is, at least as far as this derivative is concerned. So just leave it alone. You're just taking the derivative of the x squared, which is 2x, and then the y cubed just gets multiplied in. And there you go. There's your derivative with respect to x. Same thing here. If I take the derivative of the sine of something, I get the cosine of that something. It doesn't really matter what's in here, right? It's just the cosine of something. Oh, but then I got to multiply by the derivative of the inside because this is a composition, and so the chain rule is in effect. So here when we take the derivative of the inside, well, again, x is a variable. Y is just like a number. So if I take a number times x, and I take the derivative, I get just the number. So what I'm multiplying by is just that y. That gives me y cosine of xy. If I take that exact same function, x squared y cubed plus sine of xy, exactly the same way, but now I take the derivative with respect to y, I'll get a different answer. Because now, instead of considering x as a variable and leaving y cubed as just a number, leaving y as just a number, now I'm going to let y be a variable and let x be a constant. If you want to try that, you can pause the video here for a few moments, and then when you're done, we can unpause it and we'll go through it together. All right, so here, this is a constant, so just leave it alone. You're taking the derivative of y cubed. So just take your 3, bring it down, subtract 1 from the power. It's like you're back in Cal 1, 3y squared. The x squared doesn't change, you just bring it down for the ride. Same thing here. If I take the derivative of the sine of something, I get the cosine of that something. Oh, now the chain rule says to multiply by the derivative of the inside. Okay, well, let's see. This is a number times y. The derivative of number times y is just that number. And there we go. There's our derivative with respect to y. So although this is the formal definition, this is a short heuristic, shortcut that people often use to help them more quickly compute a partial derivative. Okay. Continuing with this review of Cal 3, let's take another definition. Let's say you have your function of 2 variables, x and y, like this, f of x, y. Let's call that function z. Okay, it's like saying y equals f of x. Oh, but y has already been used. Okay, so we'll use a different letter. Z equals f of x, y. Let's have that be a function of 2 variables, obviously. That have continuous first partial derivatives. In other words, you can take these 2 first derivatives, they're continuous. This would be a good example. These are continuous functions here. Let 2 variables with continuous first partial derivatives. At least as long as you're in some region of the xy plane that you care about, which we'll call R. In a region R of the xy plane. Okay. Then we'll denote by dz the product of the partial of your function with respect to x times the differential of x plus the partial of f with respect to your second variable y times your differential of y. This is the differential of z. And that should remind you of what how the differential was defined back in Cal 1, right? And Cal 1, if you had y equals f of x, well, then you wanted to find the differential of y, like, for example, you were doing like a u substitution or something like that, then you would say dy is equal to, well, you take the derivative of f dx. You're probably more familiar with seeing it as u equals f of x, so du equals f prime x dx. But same idea. The differential of your function is actually just the derivative of your function times the differential of your variable. Same thing. The differential of your function is just the derivative of your function times the differential of the variable. It's just now there's two variables, so you got to do it twice, once for each one. All right, so this is the differential of z. So for example, and let's not be inefficient here, let's just use the function from above. If I have z is equal to my function up here, x squared y cubed plus sine of xy. Then my differential of z is going to be, well, take the derivative with respect to x. So it's going to be 2xy cubed plus y cosine of xy. The entirety of that times dx. Plus your partial with respect to y, which is 3x squared y squared plus x cosine of xy, and that whole thing is multiplied by the differential dy. Okay, so now with that review of Cal 3 out of the way, and again I say review, if you haven't seen it, of course, this is not review, but this is sufficient to get us started with what we're talking about in this section, namely exact equations. So with this squared away, I'm just going to consider a family of functions, like a family of solutions, right? Oh, solutions to what? Well, they're not solutions to anything yet. Right now, let's just consider a one-parameter family of functions, regardless of whether or not they're a solution to anything. Consider a one-parameter family of functions that look like f of xy is equal to some constant. Okay? If you were to compute the differential on both sides, well, the differential of f of xy, well, we just saw the definition, the differential here would just be the partial of f with respect to x dx plus the partial of f with respect to y dy. And then if I take the differential of a constant, well, that's the derivative of a constant times, oh, and we can stop right there. That's got to be 0. Okay? So if you have a one-parameter family that looks like a function of two variables equals a constant, then the differential of both sides gives you this equation. Well, that's a differential equation, right? You have, in particular, it's a partial differential equation. You have partial derivatives here. Is this, which is a partial differential equation. Although in this course we are going to focus almost entirely on ordinary differential equations, we're going to look at partial differential equations are an entirely different course. Here we are going to look at a few instances where they are accessible. So here, which is a partial differential equation. Now, if you take a one-parameter family of functions and take its differential, it becomes this partial differential equation. The inverse is not necessarily true. Sorry, not the inverse, the converse. The converse is not necessarily true. If you have a differential equation that looks like this, that doesn't mean it has to come from this family of solutions. So, well, then when does it work like that? Like if I did have this kind of differential equation, how would I know that it came from something like this? Because if it came from something like this, well then, cool, I have a solution, right? That function is the thing that gives me this equation. Oh, but I need to be able to confirm whether or not that's true here. So we'll put this as a note here. Note: the converse is not always true. It may be, but it doesn't have to be. So what we're going to do is we're going to concern ourselves with the situation where it is true. In other words, let's figure out all the cases where something like this does come from this kind of function. That means this kind of function will be a solution. Okay, so definition. The differential equation that looks like a function, and instead of saying f, we're going to use m. Why m? M is a common choice in a lot of textbooks, both in Cal 3 and in differential equations. M of xy, if you like f, that's fine, but we're going to go with m here. M of xy dx, so something like this, this partial with respect to x, we're going to call it m like this, plus n of xy dy equals 0. This kind of differential equation is called an exact differential. Oh, sorry, I'm getting ahead of myself, aren't I? We need to define an exact differential first before we can get to an equation. So it's not an equation just yet, just an expression like this. So this differential expression, let's not get too far ahead of ourselves here. This differential expression is called an exact differential. In some region of the xy plane. If it corresponds to the differential of some function f of xy. In that region R. In other words, okay, taking the differential of this will give you this. But if you take, but if you have something like this, there's no guarantee that it is the differential of something. But if you have something like that, where it is the differential of something, well, then that's called an exact differential. That's what we're defining here. Now that we've defined that, then the second part of the definition, we can set this as part of an equation here. A first order differential equation, and this is an equation this time, of the form m of xy dx plus n of xy dy equals 0 is said to be an exact equation. If the left side of this is an exact differential. Okay, so I guess those are the kinds of equations that we want. If we have an equation like this, where this left side is the differential of some function f, then we know how to solve, because f equals a constant is our solution. Okay, but how could you possibly know that? How can you possibly know that something like this is in fact an exact differential, making this an exact equation? Well, here we have a theorem which tells us exactly how we can determine that. Let's say you have two functions. We're going to use the same names as above, m and n. Let m of xy and n of xy, let's have those be continuous and have continuous first order partial derivatives. So you can take the derivative with respect to x or with respect to y of either one, and everything will be continuous. And have continuous first order partial derivatives. At least as long as you're within some region R of the xy plane. In a region R, of the xy plane that is defined by just a rectangle. Your x is bound by some constants and your y is bound by some constants. And of course, if your functions are continuous and have continuous first order partials outside of that rectangle, that's fine too. Just minimum we need it inside of some small region. Okay. Then m of xy dx plus n of xy dy is an exact differential if and only if the partial of that first function with respect to the second variable, so del m del y, is equal to the differential of the derivative of the second function with respect to the first variable. That is to say, del n del x, like this. For those of you who have already taken Cal 3, this may sound a little familiar to you. If you haven't taken Cal 3, don't worry, you're not at any kind of disadvantage on that. But for those of you who have, or for those of you who will, just a quick note on vocabulary. This is a concept that you have or will see in Cal 3 by a different name. So note in Cal 3, this is the same as saying that m and n are the components of a conservative vector field. Are the component functions of a conservative vector field. And that function little f of xy, that function whose differential is that exact differential with m and n as its terms, this is the potential function. Of that conservative vector field. All right, so now let's see how we can actually use this. All right. All right, so for an example, let's go and solve the following equation. Let's solve x to the third plus y to the third, that quantity times dx, plus 3xy squared dy. Okay, so first of all, none of this that we've just said makes any difference if we do not have an exact equation. This has to be an exact equation, otherwise everything we've just said is meaningless, or at least it's not relevant. Okay, so for our first step here, let's go ahead and confirm that this, this is supposed to be an equation, isn't it? There we go. Let's confirm that this is an exact equation. How do we do that? Well, we confirm that the left side is an exact differential. Okay, so step 1, confirm the left side is an exact differential. You say, well, what if like all this stuff was on the right side? Okay, then look at the right side. Okay, but what if like there was stuff on both sides? Well, then bring everything over on one side so that this is 0, and then go ahead and do that. Make sure everything's on the left side first. So confirm the left side is an exact differential. Okay, and how do we do that? Well, we had a theorem that tells us how to do that. We're going to take the function which we call m of xy. That's the one that's being multiplied by dx. That's m of xy right there. And we're going to take the function n of xy. That's this other function over here. And what we want to do is we want to find the partial of m with respect to y. Okay, well, with respect to y, let's see. With respect to y, that's a constant. It's just like a number. And the derivative of any constant is 0. Plus, the derivative of y to the third, okay, well that's just like it's just the power rule. We're back in Cal 1. That's 3y squared. Okay, so 0 plus 3y squared, that's 3y squared. Now, let's go and take the partial of the second function, n, with respect to the first variable, x. Okay, well, let's see. If we're taking the partial with respect to x, the 3y squared is just like a constant. The x is the variable. And if I take a constant times x, and I take the derivative with respect to x, I get just the constant. Oh, and these are the same. So because these are the same, since del m del y equals del n del x, the left side is in fact exact. Okay, very nice. So that means we can proceed to use the theorem that we just saw on how to, sorry, I said that backwards. So that means that we've used the theorem that we just saw to confirm that we can proceed. We can now solve this using what we are looking at, an exact equation. Okay, so now the question is, how do we solve? Well, in order to do that, you have to consider what it is that we have. What we have is, there is some function, which we call f. So let's put this off to the side here. Note, our solution is going to be f of x comma y equals a constant. Okay, well, the constant is just a constant. Like we literally just write c. That's the one parameter of our one parameter family of solutions. So really what we need to do is we need to find this f of xy. Okay, but how do you do that? Well, the definition tells us exactly how. This m and this n are functions. They don't come out of nowhere. They are the differential of the f that I'm looking for. Right? Okay, so what does that mean? Well, that means that if you take the differential of your f, that's going to equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. But then that has to equal to this expression here. So that's going to equal to m of x comma y dx plus n of x comma y dy. Okay, so then that means that this m of xy, this function right here, is the derivative of f with respect to x. Likewise, that means this function here, this n, is the derivative of that same function f with respect to y. So what do? We take an antiderivative. So step number 2, let's go ahead and construct the function f. For those of you who have taken Cal 3, we're looking for the potential function of our conservative vector field. If you haven't taken Cal 3, well then we're going to take antiderivatives of these components and take the terms together. Same statement. So we're going to construct the function f of x comma y. All right. So m of x comma y, that's equal to the partial of f with respect to x. Okay, but I don't want the derivative of f. I just want regular f. Okay, then take the antiderivative. To get rid of the derivative, you take an antiderivative. Oh, but it's an antiderivative with respect to x. Okay, so dx. Oh, but this is an equation, right? Whatever you do to one side, you do to the other side. Oh, but if I take the integral of the derivative of f, I just get f. Oh, so to find f, I need to take the antiderivative of m of xy dx. You say, well, what about this other one? The other one works too. If I take n of x, oops, that's an x, n of xy dy is equal to the partial of f with respect to y, like this. Oops. And I take the antiderivative on both sides with respect to y. Okay, if this n is equal to this partial derivative, then integrating these with respect to y should give me the same result. These are equal. Oh, but if I take the antiderivative with respect to y of the derivative with respect to y, that just gives me f again. So f is equal to the integral with respect to x of m. It's equal to the integral with respect to y of n. Now at this point, some people make the mistake and say, oh, so both of them work. So just pick one and that's it. That's my answer. I just pick whichever one I like. No, you actually have to do both. Well, why? They're both giving me the same answer. Yes, they are giving you the same answer, but with respect to different variables. Well, what does that mean? Well, let's go ahead and actually start doing the construction, and then we'll see what the difference is here as we go through. So here I'll just pick on one. Let's see. So let's say I'm going to take the integral of n. Okay, well there's n. It's 3xy squared. 3xy squared. When I integrate n, I'm doing it with respect to y. Okay, so I'm just taking this bottom one here. Okay, well, let's see. We're doing things with respect to y, which means anything that's not a y is just going to be treated like a constant, just like with a partial derivative. 3x doesn't have any y's in it, so that 3x, that whole 3x is just a constant. So really, I'm just integrating the y squared. Okay, so I'm going to get 3x, constant stays right where it is. Integrating y squared gives me y to the third over 3 plus a constant of integration. Here the 3's cancel out, and I end up with xy cubed plus a constant. Okay? All right, now this constant could be the number 5. Well, why 5? Oh, just an example. It could also be the number 17. It could be negative pi. It could be 200, right? But you know what else it could be? It could be x. It could be x squared. It could be sine of x or tangent of x. It could be 1 over x to the power 19. You say, wait a minute. I thought you said it's a constant, right? Why are you saying x? X is a variable. No, it's not. You're integrating with respect to y, which means only y's are variables. This might involve an x. That's why we need to do both of these, because if there are any terms that have just x's, this integration will miss them. If there are any terms that are just y's, this integration will miss them. In order to make sure you get every possible term without missing any, you actually have to integrate both integrations. So let's go ahead and do the other one and see if there's any difference. So let's go ahead and now integrate m. Okay, m is x to the third plus y to the third. And we're integrating that with respect to x. Integrating x to the third with respect to x, that gives me 1 over 4x to the power 4. Integrating, well, this is just a constant with respect to x. So the antiderivative is just the constant times x plus a constant of integration. And again, that constant might be, 12 or negative 50, or it might be y, or y squared, or y cubed, or natural log of y. Just as long as it doesn't have an x, that's considered a constant here. So right here, this c is really a function of y. Here, this c is really a function of x. And that's why you need both of these. Notice right here, these are different. If you had done just this and said, there's your answer, you're missing a term. That term didn't show up in here. You say, okay, so then I have two answers? Well, no, we're only going to have one solution here, one family of solutions. What we want to do now is we want to take these two together and write down the union of their terms. What do you mean the union of their terms? Well, basically, take one of these, doesn't really matter which one, and just write it down completely. I'll just go from top to bottom. So I'll write this one down. So that's going to be just x times y to the third. Don't worry about the constant. We'll put that on at the very end. So just write down all the non-constant terms. So here we get xy cubed. Now come over here and find any terms you don't already have. Okay, 1/4 x to the fourth. I don't have one of those, so let's go ahead and add one of those in. Xy cubed, I already have one of those, so I don't need another one. Okay. And then your constants, because this function will capture any functions of x that this one couldn't, and because this function will capture any functions of y that this one couldn't, by putting them together, you're guaranteed that you're not missing any functions of x or y. So now this constant over here really is just a constant, like, a number. The kind of constant you're used to since like algebra. All right, so forget about the constants for a second. Write down one of these answers in its entirety, doesn't matter which one. Then come to the other one and write down any terms that are still missing. And then at the end, tack on your constant of integration here, your plus c. There you go. So now you've constructed the function f of xy. And finally, step number 3, let's go ahead and write out our solution. Our solution to our differential equation is going to be xy cubed plus 1/4 x to the fourth plus c is equal to a constant. Because after all, that's what we're looking for. We're looking for a one parameter family. Our function equals a constant. And I say, well, do I need a constant on both sides? No, you can actually put them together as a single constant. So you can just say, you can leave this one off and just put plus c over here. What I'm going to do though, is I'm going to do the following, just to highlight what we've actually done without trying to, without just glossing over it. This is a constant. Sure, it's a constant. Why do you emphasize the word a? Well, because over here I have another constant. Just because they're both called c doesn't mean they're the same number necessarily. They're both numbers, right? It's just they're not necessarily the same number. So if I take this and move it over to this side by subtracting, I get xy cubed plus 1/4 x to the fourth equals c2 minus c1. Oh, but if this is a constant minus another constant, you just get another constant. You might get 0, but probably not. These are probably not the same number. Okay, so I can't say it's 0. Best I can say is it's some number. So in the end, I get xy cubed plus 1/4 x to the fourth plus a constant. Most people, once they get this, they'll just jump directly to say, okay, let me write down everything but the constant, and then I'll have the constant on the other side. If you just jump directly from this to this, that's fine. But here I'm trying not to gloss over any steps. Here's what's happening step by step. Here are these two constants. This comes from finding the function f of xy. That constant is part of that function. Saying that function equal to a constant is a solution. That gives you this other constant. And then those get joined together and condensed. In any event, this is your result. Let's take a look at another example. This time with a little bit more information. Let's take a look at an initial value problem. So for our next example, let's go ahead and solve. This is cosine of x plus the natural log of y dx plus x over y plus e to the y dy equals 0, with the initial condition that y at 0 needs to equal to 1. Okay, we won't use this until the very end. This is our initial condition. We're going to find the general solution using the process that we just saw, and then at the very end we'll throw in our initial conditions to find a particular solution. All right, so here we go. First of all, let's go ahead and make sure that this is in fact an exact equation. So let's take the partial of n with respect to x. That is to say the partial with respect to x of this function here, x over y plus e to the y. Here the derivative with respect to x of x over a number, well, the derivative of x just becomes 1, so you get 1 over your number. Here, e to the y doesn't have an x, which means it's a constant, and the derivative of any constant would be 0. Okay, so 1 over y. Now, take the partial of m with respect to y. Okay, well that's going to be the partial with respect to y of cosine of x plus the natural log of y. Here, this doesn't have any y's in it, so the derivative with respect to y, this is just the derivative of a constant, it'll give me 0. The derivative of the natural log of y with respect to y is 1 over y. And so because these are the same, yes, our equation is an exact equation. So now we're going to go ahead and take the antiderivatives of these. Notice that when you take the derivatives, you do m with respect to y, but when you take the antiderivatives, right, the derivative is m with respect to y, the antiderivative is going to be m with respect to x. And over here, when you take the derivatives, it's n with respect to x, but when you take the antiderivative, it'll be n with respect to y. So just be mindful of that, don't get those backwards. All right, so here we go. Here's our m. Integrate with respect to x. The integral of cosine of x with respect to x would be the sine of x. Here, this doesn't have an x, so it's a constant. Antiderivative of a constant is just the constant times x. Plus c, which again, that c might include functions that involve just y. Right? Because y's are constants with respect to x. So this constant might be just like a regular number off the number line, or it might involve a y. Over here, I'm going to take the integral with respect to y of x over y plus e to the y, like this. Okay, so now if I take an antiderivative, I'm going to treat y as the variable, which means here I have constant over y. Okay, well the antiderivative of a constant over y is the constant times the natural log of y. Plus the antiderivative of e to the y with respect to y, that's just itself. Plus a constant which might be just a regular number off the number line, or which might involve x's, which are constants with respect to y. Okay, so now we're going to go ahead and join these together to find our function f. Okay, so we're going to take the union of these terms. And again, the easiest way to do that is to just pick one of them, doesn't really matter which one, and write it down in full. All right, so sine of, I'll start with the top one. Sine of x plus x natural log y. I'll leave the constant off until the very end. Coming down over here, let's see what I still need. Okay, this one provides me a xy squared as a term in my result. Sorry, xy, I don't know why I said y squared. X natural log y. Oh, well, I already have one of those, x natural log y, so don't write it down again. Over here, I've got an e to the y. Oh, I don't have one of those, so go ahead and put that in. And that's it. So this now covers all of my terms of my result. Notice here, this one potentially missed functions of y, which in fact there was. There was one term of just y that was missed. This one can potentially miss terms that involve just x. And sure enough, sine of x was missed by this one. So it's not enough to do just one or the other. You need them both and then unite their terms. Plus a constant of integration is equal to a constant of is equal to a constant. And finally, you can go ahead and bring this one over and combine them to get your result. So in the end, the solution to this differential equation ends up being sine of x plus x natural log y plus e to the y equals a constant, which makes us happy. But we're not done, are we? Because after all, that is the solution, the general solution to our problem, but we weren't looking for a general solution. We wanted a particular solution, namely the one that we get when we plug in these initial conditions. So, although this would be my general solution, now let's go ahead and plug in to find our particular solution. Here, these initial conditions are the same as saying, oh, well, if x is 0, y is 1. So let's go ahead and plug in x is 0 and y is 1. So here I'm going to have sine of 0 plus 0 times the natural log of 1 plus e to the 1 equals c. Anywhere I had an x, I plugged in a 0. Anywhere I had a y, I plugged in a 1. Sine of 0 is 0. 0 times 0, that's 0. E to the first is e. Oh, so my constant isn't going to stay a constant. Now it's an e. Okay, so again, I have a one parameter family, but to find a particular solution to the initial value problem, we now find a specific member by finding a specific value for this parameter c. So that gives me sine of x plus x natural log y plus e to the y equals a constant, which we now know is e. And this would be our particular solution. Which also makes us happy. Now, this technique that we've seen in the last two examples seems fairly straightforward, but also fairly limited. Because, after all, we began by checking that we have an exact equation. Here we have to confirm that these two are equal. But what if they weren't? What if this was not an exact expression, meaning this was not an exact equation? Then none of this would work, right? Well, that's true. You wouldn't be able to do this. However, that doesn't mean we're stuck. Let's go ahead and see if we can't build a way out of a situation like that. So suppose that you have the differential equation that looks like p of xy dx plus q of xy dy equals 0. That is not exact. So here I don't use m and n because m and n implies that they fall into the previous category since those are the symbols used. So here it's got the same pattern, but now these two do not provide an exact expression, meaning I do not have an exact equation. Because the partial of p with respect to y was not equal to the partial of q with respect to x. Okay, so what we're going to want is we're going to want an integrating factor. Just like we see with linear equations, an integrating factor can help us correct this non-exact equation so that it does fall under the previous category. So here, what do we want? We want an integrating factor which we'll go ahead and call mu of xy, same as before, such that p of xy times mu of xy dx plus q of xy times mu of xy dy equals 0. Technically 0 times mu, but, well, I guess I can write that, right? It's technically also, you multiply by mu all the way across, it's just that 0 times mu is just going to stay 0. So that this is exact. Which is true if the partial with respect to y of p of xy mu of xy is equal to the partial with respect to x of q of xy mu of xy. So yeah, these two are not equal. But what we want to do is we want to find some integrating factor so that if we multiply the entire equation all the way across by that, wouldn't affect the 0, that resulting set of expressions would then have partial derivatives like this that are equal. Okay. All right, well, how do we do that? Well, let's see. Let's actually take these partial derivatives. This is a product of two functions. To take the derivative, I would use the product rule. I would go ahead and take the derivative of the first one. So this would be del p del y. So take the derivative of the first times the second one. So times mu. Plus, now take the derivative of the second one times the first. So that'll be p times del mu del y. And then on the other side, I would do the same thing. I would use the product rule on these two because these are being multiplied just like over here. So that would be the derivative of the first one. So del q del x times mu. I'm leaving off the xy here just to save on some writing. Plus q times del mu del x, like this, which itself is a differential equation. Notice that you have an equation that has the partial derivatives in here. That is itself a differential equation. This differential equation, though, looks pretty big and kind of nasty. After I've got partial derivatives, and we haven't really talked about partial differential equations here. Not really. Okay, so then is that something that we need but is too hard to find? Well, in its current form, yes. But let's say we made a small concession. Let's say right here we want mu to be a function of x and y. But let's say we were satisfied with just one or the other. Let's say, but if mu was limited to a function of just x, oh, well, let's see. Then if I took the partial of mu with respect to y, that would just be 0, right? Because mu is a function of just x, which is a constant with respect to y. Okay, so del mu del y, it would be a function of just x, which is a constant with respect to y. So the derivative with respect to y would be 0. And this partial derivative would just be a regular derivative because it's a function of just x. So if it's only one variable, then you don't have a partial derivative, you just have a regular derivative. So del mu del x could just be written as d mu dx, just a regular derivative. That would then simplify our equation I'll call this right here equation number 1, which simplifies our equation number 1 to become, okay, well, mu del p del y, nothing changes there. But right here, del mu del y, that's equal to 0. So that's going to be p times 0, which is just 0. That goes away. is equal to mu of del q del x, which that doesn't change. But now over here, this just becomes a regular derivative. This would be q times a d mu dx, like this. Okay. Notice here, mu is a common factor to each of these, which that's what we want. We're trying to find what mu is. So let's take this and bring it over to the other side and factor out the common mu. So this would then become mu del p del y. We brought it over by subtracting, so minus del q del x is equal to q times del mu del x, like that. So now we can, let's see. We're gonna go ahead and divide q over this way, which will give me mu times del p del y minus del q del x over q is equal to d mu dx. But now, if you look at this for a moment, you realize that that's separable. This is now separable. Oops. There we go. This is now separable, which means we can use separation of variables to solve for mu. Here we get, let's see. We get the integral of del p del y minus del q del x over q dx is equal to the integral of d mu over mu. Here, the integral del of d mu over mu, that's just the natural log of mu. So the natural log of mu is going to equal to the integral of del p del y minus del q del x all over q. And finally, to isolate mu on its own, we can exponentiate on both sides. We can say e to the natural log of mu, and then we can say e to all of this stuff. And here we end up with our integrating factor. Thus, our integrating factor mu is in fact equal to e to the integral del p del y minus del q del x over q. Oh, I forgot my dx here, didn't I? Dx. And that will be our integrating factor. Here we arrived at this by making the assumption that mu was a function of only x. If at that point you change the assumption, if you come back over here and say, well, here I went ahead and said, I'm going to make a concession. This thing's hard, and I'll make it easier by limiting mu to being just a function of x. If you had made the opposite choice and said, let me limit mu to be a function of just y, you'll get an almost identical integrating factor. So here, let's go ahead and summarize that as a technique. Here's a technique to solve general equations of the form p dx plus q dy equals 0. So here, technique, making non-exact differential equations of the form p xy dx plus q xy dy into exact equals 0 into exact equations. All right. So first of all, you're going to find the appropriate integrating factor. One of the ones is the one that I just derived. The other one you could easily derive that using the exact same process we just did, except making the choice that mu should be a function of just y. So here we pick the appropriate, pick one. Find the appropriate integrating factor if the partial of q with respect to x minus the partial of p with respect to y over p, if this entire expression is a function of only y, this is the one that we did not derive because that makes the assumption that you have functions of only y, then use mu equals e to the integral of that stuff dy. On the other hand, if del p del y minus del q del x all over q, if that's a function of just x, then you're going to want to use mu to be e to the integral of that stuff. Del p del y minus del q del x over q dx. Okay. So pick the appropriate one. Now, you might actually end up being able to choose both. Right? It's possible if you compute this, that's a function of only y, and if you compute this, that's a function of only x. In which case, just pick one at random, whichever one you like. But if only this is true, then clearly you pick this, and if only this is true, then clearly you pick this. So pick the appropriate one, and if more than one's appropriate, just pick one at random. Your next step is you're going to want to multiply the integrating factor throughout. Multiply by mu, whichever mu you chose, across the non-exact equation. And finally, step number 3, you're going to go ahead and solve the now exact equation using what we saw in the previous part of this section. Solve the now exact equation. So for our last example here, let's go ahead and solve something by making it into an exact equation. Okay, let's go ahead and solve cosine of x dx plus 1 plus 2 over y times the sine of x dy equals to 0. All right, so first of all, if you see something like this, you would probably, if you didn't know ahead of time, you would probably suspect that this was an exact equation. That's why you're always supposed to check first, because maybe it is, maybe it's not. Let's see. If I take the partial of the first function with respect to y, well, that doesn't have any y's in it, so the derivative is just 0. Okay, if I take the partial with respect to x of the second function, 1 plus 2 over y times the sine of x, that's going to give me, well, this whole thing is a coefficient, it's a constant. So this is constant sine of x, the derivative would be constant cosine of x. So here I'd get just that 1 plus 2 over y would stay exactly the way it is, times cosine of x. Since those are definitely not the same, this is not an exact equation. All right, but just because it's not exact doesn't mean we cannot solve. All right, so here we go. let's go ahead and compute. Let's go ahead and compute these things. Personally, and this is just my habit, I just always do this first one. If that one's a function of just y, then I'll just use that one. I really only ever bother using this one if the first one doesn't work. But again, you can organize this however you like. You can compute both and then see what happens. You can always do this one first and then move on to this one if it doesn't work, or always do this one first and move on to this if it doesn't work. It really doesn't matter. You'll get the right results either way. All right, so here we go. So now let me go ahead and find del q del x minus del p del y all over p. Okay. All right, so that's going to be, well, let's see, del q. So this was p right here, the first function, which is multiplied by dx. We call that p. This whole thing over here that we're multiplying by dy, we call that q. So the derivative of q with respect to x, well, we just found that a minute ago. That was 1 plus 2 over y cosine of x minus the derivative of p with respect to y. We also just found that a moment ago. That was 0. And then we're going to divide that by the original p, by the original function cosine of x. Oh, well here, 0 doesn't do anything, so you could ignore that. Cosine of x divides cosine of x, and so all you're really left with is 1 plus 2 over y. Okay, but according to our technique, if you find del q del x minus del p del y over p, if you find that, and that's a function of only y, which, yep, that's a function, doesn't have any x's, just y, then you're going to use this as your integrating factor. All right, so let's give that a try now. So our mu is going to be e to the integral of that thing we just found, right? This thing we just found here. That's going to be 1 plus 2 over y, and we're going to integrate that with respect to y. There we go. So this will be our integrating factor, e to the integral 1 plus 2 over y dy. All right, so let's go ahead and integrate that. That's going to be e to the, if you integrate 1 with respect to y, you get 1y. If you integrate 2 over y with respect to y, you get, well, you get a plus there. 2 integral of 1 over y is the natural log of y, like that, plus a constant of integration, like that. All right, so now the way exponents work, you may remember that if you have something like e to the a times e to the b, you multiply two things that have the same base by adding their powers. Well, that's what you have here. You have the sum of powers. So you can separate that as a product. So this is e to the y times e to the 2 natural log of y times e to a constant. Okay. Now, e to a constant is itself just a constant. All right, e to the first power, e to the second, e to the fifth, e to the 90th, whatever, that's just a constant. So here, this itself will be just a number. Since it's being multiplied, I like to call it m. Right? If you want to call it c, you can, but I'll call it m. So this is m. And let me call it M1. There might be other M's later. So in fact, I probably should have called that one C1 as well. There may be other C's later. So M1, let's see, that's e to the y. Right here, if I have e to the 2 natural log of y, I have a property of logarithms that lets me pull up the constant as a power. So this is equal to e to the natural log of y squared. And now those two divide out, or not divide out, those two compose away, and you're left with just y squared. So here e to the 2 natural log y is just y squared. And then here I've got e to the y, which doesn't simplify, it just stays e to the y. So some constant m1, y squared e to the y, that is going to be my integrating factor. Now with an integrating factor, these are not your solutions. All right, so you don't need a whole family of them. An integrating factor, you just need an integrating factor. Here, what this tells you is that anything that looks like this will work as an integrating factor. So here, this M1, I could choose it to be 7, and that would work. That would be a valid integrating factor. I could choose 12, I could choose 19, I could choose negative pi. So let me be nice to myself. I only need one integrating factor. Any number here will work. So let me choose the simplest number that I can use here, and that would be 1. You say, well, wouldn't 0 be easier? Yes, but you're about to multiply by this, and if you pick 0, you're going to get 0 plus 0 equals 0, which is true, but doesn't help you solve anything. So here I'll choose 1. By choosing 1, and remember, you can't do this for solutions. You can only do this for integrating factors. But for an integrating factor, you're free to choose whatever constant is convenient. And again, it doesn't have to be 1. You could have chosen 75 if you really felt like it. By choosing m1 equals 1, we will get the integrating factor mu equals 1y squared e to the y. So what we're going to do now is we're going to go back to our original problem, and we're just going to multiply all the way across by that integrating factor there. Okay, so I'm going to have cosine. I'm going to just rewrite my problem. Cosine of x dx plus 1 plus 2 over y sine of x dy equals 0. I've just gone ahead and written down the original problem right here. Now I'm going to multiply all the way across by mu, which is y squared e to the y. So multiply here by y squared e to the y, multiply here by y squared e to the y, and multiply here by y squared e to the y, even though it doesn't actually make a difference on this side, since it'll be 0 anyway. Okay, let's see, nothing simplifies here, but here I can distribute. So let me get y squared e to the y cosine x dx plus, let's see, I think I'll leave the e to the y on the outside. Let me just distribute this because this will simplify a little bit easier. So I'll have e to the y times y squared plus 2 times y sine of x dy. Assuming we haven't made any mistakes, this is now guaranteed to be exact. All right, so right here, this is now an exact equation. If you're not certain, of course, you can always check by taking the partial of this with respect to y, take the partial of this with respect to x, but yes, in fact, they both will work out to be the same result. These are these right here are going to give you an exact expression, making this an exact equation. So finally, we can go ahead and solve here. Let me take my integral of my m, and I can't call it m now because this is exact. Integral of m dx. Oh, now I'm extra glad I called this m1. Otherwise, I'd be using the same symbol here. So the integral of m dx, which is to say the integral of y squared e to the y cosine of x dx. Also, let me go ahead and take the integral of n dy, which is to say the integral of this stuff with respect to y. And that'll be e to the y times y squared plus 2y sine of x dy. And let's go ahead and integrate these things here. All right, so this first one here, this is a constant with respect to x. So really this is just constant cosine x. The antiderivative would be constant sine of x. So y squared e to the y sine of x plus a constant which might include functions of y because this only covers x's. Okay, now this one seems very complicated till you realize, okay, well sine of x is a constant, so I could ignore that. Oh, yeah, but that's still pretty complicated. Yeah, but then you realize that this one is the derivative of that one. What do you mean? I mean this one's the derivative of that one. So when you expand this, we can write this as integral e to the y times y squared. Oh, let me put the y squared first to make this look a little more obvious. So this would be y squared e to the y plus 2y e to the y sine of x dy. Yeah, so this is the result of having used the product rule. Notice, I can write this as just the part in the parentheses. I can write this as the derivative with respect to y of y squared e to the y. Because after all, if I take the derivative here, it would be the first thing times the derivative of the second, derivative of e to the y doesn't change, plus you take the derivative of the first one, derivative of y squared is 2y, times the second. Again, e to the y doesn't change. So this right here is the derivative of this product. Sine of x is a constant. In fact, since it's a constant, I can even pull it to the outside. Doesn't that look weird to pull out something with a variable out of an integral? But it's not a variable, it's a constant. So now I have the integral with respect to y of the derivative with respect to y of this function. Oh, well then that just gives me this function, doesn't it? So here I end up with the sine of x times y squared e to the y. Plus a constant which might, since I'm integrating with respect to y, that it might involve an x. But notice here, these are exactly the same. So whatever this one has, this one already has, and vice versa. So we can put this together as our final result here. So our solution is just that function there. Y squared e to the y sine of x plus a constant equals a constant. Whatever, we can put the constants together and just say equals c. And that is now the solution to our original non-exact equation, which we get by first making it exact and then solving via that technique. Alright, so that's it for that topic. That's it for that section. If anybody has any questions, comments, or problems, please reach out. And I hope everyone has a nice day.